the rule we have considered just now is that if f of t is multiplied by an exponential function of time, that corresponds to a shift in the frequency domain. We have a dual rule which corresponds to shift in time domain, and that corresponds to multiplication by an exponential function in the frequency domain. This is corresponds to multiplication by an exponential function in the frequency domain, that is the complex frequency domain, or in S domain. Let me first put down the rule and then we will try to demonstrate that. Suppose f of t and f of s form a transform pair, and let me assume that I will also put u of t to make sure that it is a causal function. Suppose I have this is f of t u t. Now, let me say that I translate this, I delay this function of time by an amount of tau seconds. So, instead of starting from t equals 0, it starts from here and it goes like this. So, this is tau. The same function is delayed by an amount tau. Therefore, we can describe this as f of t minus tau u of t minus tau. This is the description of this function. Everything is delayed by tau seconds. Whatever value this function takes at t1, this will take at this t1 plus tau seconds in the second case. It is delayed. So, what is the Laplace transform of, given the Laplace transform of this is f of s, we ask the question what is the Laplace transform of this. So, f of t minus tau u of t minus tau has the Laplace transform, it turns out to be e to the power of minus tau s f of s. So, a shift in the time domain corresponds to multiplication by an exponential factor in the frequency domain. A delay by tau seconds involves multiplication in the frequency domain by e to the power of minus tau s. We take tau to be greater than 0, that is, this corresponds to a delay. Now, the proof of this is quite straightforward. So, we are interested in finding the Laplace transform of f of t minus tau u of t minus tau, and this must be multiplied by e to the power of minus s t dt. That is what we are interested in finding. Now, since the variable of integration is t, as long as t is less than tau, u of t minus tau is 0. So, as long as t is less than tau, the argument is negative and this makes it 0. Therefore, I can as well start the integration from tau infinity of f of t minus tau u of t minus tau e to the power of minus s t dt, because this factor makes the integrand 0 for values of t up to equal tau. Therefore, f of t minus tau u t minus tau e to the power of minus s t dt. And for values of t larger than tau, then this is going to be 1. So, you may as well leave it like that, or you may, even if you want to keep it, no harm in there, no harm is there. Now, let me put here t minus tau as, let us say, x. Then this is f of x, u of x, e to the power of minus s, t equals tau plus x, x plus tau, and the dt equals dx. And the range of integration, now when t becomes tau, x becomes 0, so it starts from 0, and when t equals infinity, x also will be infinity because tau is finite. That is what we are having. Now, this integral involves the variable of integration x, this tau is a constant, therefore, I can write this as e to the power of minus s tau 0 to infinity of f of x e to the power of minus s x dx. And what you are having here is indeed, you can also consider this 0 to infinity f of t e to the power of minus s t dt. So, that is the Laplace transform of f of t. Therefore, the result is e to the power of minus s tau f of s. This is what we mentioned here as the Laplace transform of f of t minus tau u to t minus tau. That is the proof of this. This particular rule is very, very important, because it comes in very, very handy in finding out the Laplace transforms of various typical functions that we handle, like pulse functions and so on. As we will take some examples to illustrate this. Let us see, let us work out some examples. Let us consider first of all a pulse function 0 to d, it exists from 0 to d, value a here, this is f of t. Now, you can always consider this pulse to be a step function of amplitude a starting at t equals 0 plus another step function of amplitude minus a starting at time t equals d. If you add these two step functions, one regular step function starting at t equals 0, another a delayed step function starting at t equals d, adding up these two you will get this. And now, we know the Laplace transform of this. This will be, this is a not a unit step function, but a step function of amplitude or magnitude a. Therefore, the Laplace transform of this is a upon s. Now, the Laplace transform of this is, how do you describe this? Is this minus a u of t minus d. This is the expression for this second function, whereas the first function is a u of t, and therefore, it had this Laplace transform. All we are now doing is, instead of t, you are delaying this by d seconds. Therefore, the Laplace transform of u of t minus d is 1 over s e to the power of minus ds. You have to multiplying this by a minus a. Therefore, the Laplace transform of this is minus a by s. This would have been the Laplace transform if this delay did not occur, but because the delay you have e to the power of minus ds. Therefore, the Laplace transform of this is the sum of these two. So, you have a upon s into 1 minus e to the power of minus ds. That is the Laplace transform of this. So, you observe that whenever you have discontinuities in the function and type of pulse functions like this, they can quite conveniently handled by using this property of the shift in time domain. What difference it makes in the transform domain is, all that it means is you are multiplying by an exponential factor e to the power of minus s times the delay that is involved. Let me take another example. B. Suppose I have 1/2 cycle of a sinusoid, just this 0 to t naught upon 2, and of course, we will assume that omega naught equals 2 pi upon t naught. So, we want to find out the Laplace transform of this, a single loop of a sinusoid. Now, this can be considered to be a regular sinusoid sin omega naught t u t plus, suppose I delay this sinusoid by 1/2 period. So, I get another sinusoid like this, and this would be sin omega naught t minus t naught upon 2 delayed by that amount u of t minus t naught upon 2. That is a delayed sinusoid. Now, if you add these two, this negative loop is cancelled by the positive loop, this positive loop is cancelled by the negative loop, and so on. If you add these two, this is what you get, right? And therefore, if you add the Laplace transforms of these two, you will get the Laplace transform of this by the linearity principle which we talked about. Okay. Therefore, the Laplace transform of this single loop will be the Laplace transform of this, which is omega naught over s squared plus omega naught squared, plus the Laplace transform of this, which is obtained by multiplying the Laplace transform of this by e to the power of s times minus s times the delay that is involved. Therefore, e to the power of minus s t naught upon 2. That is what you are having. That is the Laplace transform of this single loop. You do not have to do any integration. The advantage of knowing all these properties is that whenever you are having functions of this type, if you cleverly manipulate this, you do not have to carry out this integration to find out the Laplace transforms. From the Laplace transforms of known functions, you can construct the Laplace transform of this purely through algebraic procedures as shown here. So, let us move on. Let me consider two further examples. One, suppose I have a triangular pulse function 0 to 4 seconds, it lasts, it reaches a value of 8 at t equals 4, and we would like to find out the Laplace transform of this. Now, once again we do not have to do any integration, because we know the Laplace transforms of ramp functions and step functions. So, we would like to decompose this function in terms of appropriate step and ramp functions. Let us see how we do that. Suppose we describe this portion by a ramp function, then you have a ramp starting at 0, reaching the value 8 at time t equals 4, and this would be described as 8 units, it jumps by 8 units in 4 seconds, therefore, it is a slope of 2. So, this will be 2 times RT, that would be the ramp. Now, this ramp describes the actual behavior of f of t up to t equals 4 seconds, but at this point we must nullify whatever is left beyond 4. So, to do that, we introduce a negative ramp here at 4 seconds of the same slope, so that the growth is arrested. Therefore, this would be having the negative slope of minus 2, and then it starts at t equals 4 seconds. So, that would be the description of this curve. Minus 2 RT minus 4 would be a negative going ramp with a slope of magnitude 2 starting at t equals 4. If you added these two, what you would get is this one plus a constant here, because whatever increase here is cancelled by the increase here. So, what is left by adding these two curves is not only this triangular pulse, but also a kind of constant, a step here. So, we should cancel that step as well, and the magnitude of the step is 8 units and starts at 4. So, in addition we need to have a step here, a negative step. So, this will be described as minus 8 u of t minus 4. So, if you added these three characteristics, then you would get this pulse. You have a ramp function to start with, a negative ramp to arrest the growth, and then afterwards whatever amount to which it has grown must also be cancelled out, that will be minus 8 u to the power of t minus 4. Now, we know the Laplace transforms of these three type functions. So, the Laplace transform of this would be the Laplace transform of the ramp, which is 2 upon s squared, and then the Laplace transform of this ramp is if this is 2 upon s squared, this is 2 upon s squared times e to the power of minus 4s, because the same ramp with a negative sign and delayed by 4 seconds. Therefore, minus 2 upon s squared e to the power of minus 4s. That would be the Laplace transform of this delayed ramp. The Laplace transform of this step function is minus 8. It would have been, if we had started at t equals 0, it would have been minus 8 by s, but since it has been delayed by 4 seconds, you have to write minus 8 by s e to the power of minus 4s. That is what you are having, 2 upon s squared times 1 minus e to the power of minus 4s minus 8s over e to the power of minus 4. This is the how it goes. Second example. Now, you must be careful when we are talking about the notation for the delayed time functions, that you f of t minus tau times u of t minus tau is gives a proper expression for the delayed time functions. To distinguish between other possibilities, let me take a set of examples. This would be t u t. Suppose f of t is t, then this is 2 u t. Suppose I write t minus 1 u of t. What does it mean? This is not a delayed function, because u of t has not been replaced by u of t minus 1. T minus 1 u t would be this function 1. This will be at t equals 0, it would have been minus 1. That is what it would be. The same slope, of course, but it does not start at t equals 1. This is not a delayed version of this. Important to recognize that. Suppose I have t u t minus 1. So it's a, this is t u t, but t is multiplied by u t minus 1. That means this function t is multiplied by a step which is starting at t equals 1 at this point. Therefore, this would have been t, but this portion has been cut off. So that would be t u t minus 1. So this is 1, and here it is. That is t u t minus 1. On the other hand, if you have t minus 1 u t minus 1, this would be whatever sequence of values this had, it takes 1 second later. Therefore, this is a proper delayed function. The same function is delayed by 1 second. Therefore, that could be. So you see, you have presumably these are delayed functions, but they are not the delayed functions of this. So we must be careful in distinguishing between the various functions that are covered by these expressions. Now, the Laplace transform of this is, of course, 1 over s squared. It's very clear. Now, this is a delayed function. Therefore, you can immediately write 1 over s squared e to the power of delay is 1 second. Therefore, 1 over s squared e to the power of minus s. There is no problem about that. Now, what about this? T minus 1 u t can be written as t u t minus u t. T u t, that means you have t u t, you remove one unit value at every point of time. This is what you get. T u t would be this curve parallel to this. If you remove u of t from that, this curve results. Therefore, the Laplace transform of this is 1 over s squared minus 1 over s. The Laplace transform of t u t is 1 over s squared. Laplace transform of u t is 1 over s. Now, as far as this is concerned, t u t minus 1, you can think of this as t minus 1 u t minus 1 plus u t minus 1. If you add these two, that is what you get. So, t minus 1 u t minus 1 is a proper delayed function of this. Therefore, this is 1 over s squared e to the power of minus s, and u t minus 1 will have the Laplace transform 1 over s e to the power of minus s. So, you can see that these three functions have different Laplace transforms. they are not the same time functions, of course, therefore, we expect the Laplace transforms to be different. You can also see this as this can be thought of as a delayed step plus a delayed ramp. That is what we are having, delayed step plus delayed ramp. Right. Now, before we proceed to a discussion of another property, let me caution you about one possible pitfall that one might fall into. We agreed that if the function f of t is delayed by tau seconds, f of t minus tau, this will have e to the power of minus tau s f of s. That is the Laplace transform of this. Now, the question that we can ask is, what happens to advance in time? Suppose you have a function f of t, you advance it. So, that means f of t plus tau, where tau is once again considered to be positive. Does this mean that this will be e to the power of tau s f of s? This is the question that we would like to ask. We must exercise caution in applying this rule. Why? When you advance a time function, what happens is, when you push some part of the time function to the negative values of time, then a part of that function can get lost. Therefore, it is not, if it is delayed, then the same functional variation whatever we had f of t ut continues. But if you advance it in the negative direction, that is a negative direction of time, that means a part of the function can get lost, and therefore, whatever is left may not have a complete replica of the original f of t ut. Therefore, this rule may or may not work. So, one must be careful in this. As far as Fourier transforms are concerned, the delay, if you have a delay or advance by tau seconds, it is multiplied by e to the power of j omega tau or e to the power of minus j omega tau, as the case may be, without any difficulty, because the Fourier transforms handle time functions which exist for negative values of time as well, but not Laplace transforms. So, let me illustrate this by means of an example. Suppose f of t is like this. This is 2 seconds, and then I have, let us say, g of t, which is obtained as f of t plus 1. So, f of t is a delayed step function starting at 2 units, and g of t is advanced by 1 second, this is f of t plus 1. The Laplace transform of this is obviously 1 over s e to the power of minus 2s. The Laplace transform of this is 1 over s e to the power of minus s. Therefore, we can see in this case that g of s is f of s multiplied by e to the power of s corresponding to 1 second advance. Therefore, this rule works quite well here. But because when you are advancing this, nothing of this function is getting lost. Right? Now, suppose you have the same f of t, and now I say g of t now is f of t plus 3. That means this is advanced by 3 seconds. That means it is like this. When you take the Laplace transform of g of t, however, you ignore this portion for negative values of time and take account only of this. So, this portion is gets neglected, it gets lost, this portion. So, we would say g of s is the Laplace transform. This is, of course, I am taking all this of unit magnitude. So, we will take this is the Laplace transform of a unit step function, this is 1 over s. Now, f of s as 1 over s e to the power of minus 2s. The function is advanced by 3 units. Therefore, this is not equal to 1 over s e to the power of minus 2 s, which is the Laplace transform of f of s. The advance corresponds to 3 s. So, this would be what we would have expected if the same rule applied for advanced functions as it would apply for delayed functions. So, if you had multiplied by e to the power of 3 s, you would have got 1 over s e to the power of s, but it is not equal to 1 over s. Therefore, this is not equal to this. This is incorrect expression for this as far as the Laplace transform is concerned. Let me take a third example. Suppose I have f of t, which is a ramp function. So, f of t here will give me 1 over s square. Suppose I advance this by one second. So, this I will call it g of t. Now, once again, when you are considering the Laplace transform of this portion is ignored, and you are considering only this portion, and that is equal to a step function plus a ramp function of unit slope. Therefore, the Laplace transform of this g of s would be 1 over s plus 1 over s squared, and this is certainly not equal to 1 over s squared multiplied by e to the power of s corresponding to the advance. Therefore, this is not equal to this. So, when we are advancing time functions, one has to be very careful whether this particular rule like this will apply or not. If the advance corresponds to a situation where no portion of the original function has been truncated, as it has been in this case, then that rule will apply. But in other cases like this, which is more usually the situation, this rule will not apply. So, as far as this rule that we have talked about is primarily intended for delayed time functions, when it is advanced, one has to take it with a pinch of salt. The next property we will talk about is scaling. What we mean by this is, if f of t and f of s form a Laplace transform pair, then f of a t, where a is a positive constant, that means you scale the time events, you make them appear faster, f of a t. This corresponds to a Laplace transform 1 over a f of s over a is the rule that comes. So, scaling in time domain also corresponds to scaling in the frequency domain, but in the inverse fashion. If you make events faster, that will be slower and vice versa, but of course with a multiplying factor here. Proof. Zero to infinity of f of a t e to the power of minus s t dt. That will can be written as, if you put a t as x, this will be f of x e to the power of minus s x upon a dt equals dx upon a. So, I will pull this outside, and when t equals 0, x is 0, when t equals infinity, x is also infinity. So, all we are having is f of x instead of e to the power of minus sx, you have x upon a or s upon a. Instead of st, you have s upon a times x, s upon a times t. X is a dummy variable, you can replace it by t as well. Therefore, what you are having here is, instead of s, you are really having s upon a times this x, which is the variable of integration. So, obviously, this is the Laplace, if f of s is the Laplace transform of f of t, this would be f of s upon a. Therefore, 1 over a f of s upon a. That is what we have proved here. or you can put this, or A times f a t as the Laplace transform of f, which is the same thing. Now, this particular rule comes in handy sometimes in numerical working like this. Let me illustrate this by means of an example again. When you have large numerical constants, sometimes we can avoid this by type suitable scaling. Find the inverse Laplace transform of 1 over 10 to the power of 4 s squared plus 10 to the power of 2 s plus 1. Suppose I ask this question, what is the inverse Laplace transform of this? We have to find this out. So, we can scale this in the frequency domain in this fashion. 1 over 10 to the power of 4 s squared plus 10 squared s plus 1 can be written as 1 over s upon 10 to the power of minus 2 whole squared. Suppose I divide this by the same thing, 10 to the s squared divided by 10 to the power of 4, or 10 to the power of 4 if you carry it in the denominator is 10 to the power of minus 4. The same thing can be expressed in this fashion, and then this can be written as again s upon 10 to the power of minus 2, which is same thing as 10 squared times s plus 1. So, if I had scaled this s by a factor such that s upon 10 to the power of minus 2 is replaced by s, then this is 1 over s squared plus s plus 1. We know the Laplace transform, inverse Laplace transform 1 over s squared plus s plus 1. Once we know that, we can find the inverse Laplace transform of this by applying the scaling rule. Let us see how we do that. If this had been simply 1 over s squared plus s plus 1, instead of this s upon 10 to the power of minus 2, we would have written this as we have already mentioned as s plus half whole squared plus root 3 upon 2 whole squared. Yes, and this would have been 2 upon root 3 times root 3 upon 2 over s plus half whole squared plus root 3 upon 2. Why I put this root 3 upon 2 here is because this is of the form omega naught over s plus alpha squared plus omega naught squared. So, this particular Laplace transform would be having its inverse Laplace transform 2 upon 3 e to the power of minus t upon 2 sine root 3 upon 2 t. That is the, of course, u of t will always be there. This is the inverse Laplace transform of this. But now, if this is f of s, what we have having here is instead of s, we have s upon 10 to the power of minus 2. So, we have s upon 10 to the power of minus 2. That is what this expression is. Now, if you go to this rule here, f upon s upon a will be a times f of a t. A in our case happens to be 10 to the power of minus 2. So, since we know f of t, we can find out a times f of a t. This corresponds to a times, this is f of t. If this is f of t, this is a times f of a t, where a equals 10 to the power of minus 2. So, if you substitute that, you will have 10 to the power of minus 2, 2 upon 100 root 3 e to the power of minus t upon 200 a t sine root 3 upon 200. That is the inverse Laplace transform of this. So, this scaling rule helps us to make the coefficients change the scale of the coefficients so that we can handle convenient numbers instead of sometimes unwieldy numbers like this. We can often take advantage of this rule. Remember this is in accordance with what we discussed in the case of Fourier transforms. If you make the events faster in time, this is equivalent to increasing the frequency. That is, if you scale t in one direction, in the frequency it goes in the other direction. If t is replaced by 2t, s is to be replaced by s upon 2. So, if you compress events time to take them occur at a faster time, the frequency spectrum increases. So, you need to encounter higher frequencies. On the other hand, if you spread out in the time domain, then in the frequency domain it gets compressed, the higher frequency components become smaller. So, in this lecture we covered 3 important properties of the Laplace transform. The first one we considered was when f of t function of time is multiplied by an exponential function of time e to the power of minus alpha t, for example, then in the frequency domain it corresponds to a shift in the frequency variable, that is s will be changed to s upon alpha. And the second important property which we discussed was when you shift a time function in time delayed by tau seconds, the corresponding effect in the transform domain is multiplication of f of s by e to the power of minus s tau. And we saw the ramifications of this if you try to use this to apply to advanced functions. We said when you advance a time function by tau seconds, it may or may not correspond to an f of s which is multiplied by e to the power of s tau. In some cases it may, in most of the cases it may not, because part of the time function may get lost in the process. Lastly, we considered the scaling in time domain, which corresponds to also to scaling in frequency domain. If you are scaling up in time domain, it will be scaling down in the frequency domain by a factor a. Of course, there will be also a change in the multiplying constant. In all these 3 cases, we have considered various examples which illustrate the usefulness of these 3 properties when you are evaluating either the forward Laplace transforms or the inverse Laplace transforms. We shall pick up at this point in the next lecture.